Hello everyone. In this video, I'll show you how to create synthetic data for your computer vision applications using Unreal Engine 4. We'll make use of NVIDIA Deep Learning Dataset Synthesizer (NDDS) plugin. But as you will see, the original repository supports up to only Unreal Engine version 4.22. To take advantage of the free, high-quality content in the marketplace, we need to be able to use Unreal Engine 4.27. So, we'll make use of this fork of the repository which supports up to Unreal Engine 4.27. You can find the link in the description. Clone the repository and check out the correct branch with the command shown on the screen. This is assuming you have installed Git on your Windows machine along with Git LFS. Open Epic Games Launcher and launch the engine version 4.27. It might take a while to launch. Once the engine has launched, click on Browse and browse to the location where you cloned the repository. Click on the NDDS.u project and select Open. The first time the project is opened, it will ask you to rebuild it. Click on Yes to continue. It might take a while to rebuild the project. Once the project has been rebuilt, you will find the test capture level open. Let us rebuild the lighting for this level. You can dismiss these map check issues for now. Although this is not a beginner-level Unreal Engine tutorial, you can find the keys I am pressing by following the keystroke visualizer in the top right corner. Let's take a closer look at the scene capture actor in this level, which represents the camera that is used to record data for this level. Here is the list of data which can be extracted using this actor. We have the object data, color, depth and segmentation annotations. We can right-click on the actor in the scene and click on Browse to Asset to find its location in the content browser. We can later drag this actor into our own custom scene from this location. To see the plugin content, make sure that Show Plugin Content is checked in the View options. Sometimes, you might need to check and uncheck the Show Engine Content to see the plugin content. Going back to the scene capture actor, we can have a look at the various settings available to us. To select the path where the generated data will be saved, click on Scene Data Handler. Click on Save Path, and click on the three dots next to Root Capture Directory Path. Browse to the path where you would like to save the data. For directory conflict handle type, you can select to either overwrite, remove the existing files, or create a new directory for every iteration with a new timestamp. If you would like to start capturing data as soon as you press play, you can set Auto Start Capturing to True. You can also set the max number of frames you would like to capture. For this tutorial, we'll set it to 100. When we press the play button, we can see this view, where a number of objects are moving around in the scene. Click on Start to start capturing these frames. The scene capture will stop once the max number of frames have been captured. Click on Stop to stop the simulation. Open the directory where you had chosen to save the data. You find the newly captured data inside a directory named after the name of the level. We can now see the data captured by the scene capturer. We have the RGB images, along with the instance segmentation images, class segmentation images, and the depth images in various formats. We can notice that the objects in each image are in different locations. Each image has a unique background as well. The domain randomization BPs included in this plugin help achieve this. We will see how to use them later on in the video. For now, let's open the JSON file associated with one of the images. This file contains the class names of the objects in the image, along with their 2D and 3D bounding box annotations and other related information as well. Here, we can see that one of the annotated objects is named SM Rail Rig Track. By default, the class name is set by the name of the mesh. The mesh is assigned to the test annotated actor BP. The 2D bounding box annotation for this object in this image is specified here. To train a custom object detection model, you can convert these annotations into the format specified by the framework of your object detector. We also have the 3D bounding box annotation, which can be used to train a 3D object detector. This image has the instance segmentation annotation for one of the objects in the scene. Let's see how to create our own scene to collect data. Click on File, click on New Level, and click on Default. Here, we have an empty scene. We can start building it to create our own custom data. We will use Scene Capture All feature in our scene. We also have Scene Capture Simple BP, which captures a subset of the features captured by Scene Capture All feature. Feel free to use this camera instead. We can always select the features we want to extract in either case. Let's position our scene capture actor in the center of the level. We will position the camera such that it is facing the floor at an angle. Let's bring a table into our scene. In the content browser, search for table and drag the table into the scene. The table is available in the ArchVis pack. If you don't have it imported, you can add it from the marketplace. We'll soon see how to add free content from the Unreal Engine marketplace. We can pin the camera view while we adjust our scene. Let's add a material to our floor. We'll add this wooden material to our floor mesh. We will now look for some free content from Unreal Engine to add to our scene. Go to the Epic Games launcher. Click on Marketplace. Click on Free, and then on Epic Games Content. We can see that Epic Games provides a lot of high-quality free content which can be added to our scene. In the search bar, search for Twinmotion. We'll use the Twinmotion High-Tech Pack for this tutorial. As we can see, these high-quality contents are only available for Unreal Engine version 4.27 and higher. Click on Add to Project and select our NDDS project from the pop-up screen. It can take a few minutes to add this content to our project. Once the process is complete, we can see our new assets in a new directory under Content. Let's drag this laptop into our scene. We'll rotate and place it in an appropriate location. Let's bring a speaker into our scene as well. If we press play now, we see that we don't have the same interface to start collecting data as in the test capture level. So first, we need to go to World Settings, and under Game Mode, set Game Mode Override to NV Scene Capture Game Mode BP. Now if we press play, we have the interface to start collecting data. But before starting, let's go over our scene capture settings. We can select which features we want to capture here. We can specify the captured image size, camera intrinsics, and many other things. As before, let's set the path for the captured data. Press on play and click Start to start capturing data. Looking at the captured data, we can see that the objects are static in the images. Here we have the class segmentation annotation images and depth images. But looking at the JSON file, we can see that the 2D and 3D bounding box annotations have not been captured. To capture these annotations, we need to use the DR annotated actor BP. Before proceeding, let's save this level as custom map. To find the DR annotated actor BP, go to Content Browser. Click on Domain Randomization DNN Content. Blueprint. Let's drag the DR annotated actor BP into our scene. Currently, this BP looks like an empty volume. Let's assign an object to its mesh field. Right-click on the laptop mesh and browse to Asset. Select the laptop in the Content Browser. Find and click on the DR annotated actor BP in the world outline. In its static mesh field, click on the left-facing arrow. It assigns the selected asset from the Content Browser to this field. We can copy the location of our original laptop and assign it to the new DR annotated actor BP. We might need to adjust it since the center of the BP is different than the laptop mesh. We can delete the original static mesh now. Press End key to place the laptop on the table. We can duplicate our new BP and repeat the same steps for the speaker as well. Let's click on play and test our new setup. In the simulation, we can see that although the objects are now moving, their movement is very random. Looking at the generated images, we see that in most of the images, the object is not visible. To constrain the movement of our objects, we need to assign a volume for their movement. In the left search column, look for trigger volume. Drag the trigger volume into the scene. Let's resize this volume to fit the size of the table. We can use the different orthographic views for this. Let's go back to the perspective view. Click on one of our DR annotated actor BPs. In the detail view, click on Random Movement. Under Random Movement component, uncheck the Related to Origin Location option. Click the drop-down menu next to Random Location Volume. Once it's activated, select the trigger volume we just created. Let's rename this trigger volume as Object Movement Volume. Let us repeat the steps for the second DR annotated actor BP. Click on play. We can see that the object movement is now constrained over the table. Going through the images, we see that the objects have random rotation in all axes, which is very unlikely in a real-life scenario. To fix the random rotation, select the BP. In the detail view, click on Random Rotation. Under Randomization, set the pitch and roll ranges to 0. For the yaw range, let us check the current rotation of the actor and assign the range around that value. Let us repeat the steps for the second DR annotated actor BP. In the simulation, we can see that the object's rotation is now constrained. In the generated images, we see that although the object's movement and rotation is constrained, they pass through each other in the table. This is very unlikely in the real world as well. To fix the issue of objects passing through each other, select the DR annotated actor BP. In the detail view, select random movement. Under random movement component, make sure the box next to check collision is checked. Repeat the same steps for the second DR annotated actor BP. Now, when we press play, we can see that the objects are no longer passing through each other. We can confirm the same in the generated images as well. In addition to the above step, we can also set the collision settings for the BPs to block all actors. We can further improve our scene by adding walls, lighting and other details to make the scene look more realistic. For now, let's see how we can use some free content with a prepared scene. Open the Epic Games launcher. Click on Marketplace. Search for room and select the free filter. We will use the Edith Finch house and common areas content for this tutorial. Add the content to cart and finish the purchase procedure. Next, let's add the content to our project. It can take a few minutes to add this content to our project. Once added, you can find the new content inside a new directory under Content. Inside F first floor, let us open the first floor map. Once loaded, wait for a few minutes to let the shader compiling finish. The scene is pre-built and lighting is well lit. And it comes with many high-quality assets. Let us add our scene capture camera to this scene to start collecting data. Next, we will add a trigger volume to the scene to constrain the object movement. We can now bring in the DR annotated actor BP into our scene. Next, find the book asset in the content browser and assign it to the BP's mesh field. Let's do the same for the plate asset as well. We'll next add the constraint for random movement to our DR annotated actor BPs. And add the check collision option as well. Let's limit the rotation as well. In the simulation we see that the objects are still passing through each other, even though the check collision option is checked. Let's check if these meshes have a collision mesh or not. In the collision settings of our BPs, let's set the collision presets to block all actors. There are still some instances where the objects overlap as the space is very limited. Let's clean up our scene a little bit. We can also change the size of our captured images. Let's set the image size to 1024 by 768. As we have added a few more actors and rearranged the scene, we should rebuild the lighting to remove these artifacts. Next, to visualize our newly generated data, we will use another repository by NVIDIA. Go to this repository in your browser. Link is in the description. We can install the visualizer with pip. Upon installation, go to the directory containing our generated data and use the command nvdu_vis and path to the directory to launch the visualizer. This tool will help you visualize your synthetically generated data. I hope you enjoyed the video. Thank you for watching.